Hi, everyone. Thanks for joining today. We're going to give it just a moment for everyone to jump into the Zoom before we get started today. Looks like we have a good amount of people logging on. We're just going to wait one moment, give a chance everyone to log into the Zoom, and then we'll get started. Great. Looks like we have a good amount of people. So hi, everyone. My name is Courtney Brown. I'm a senior marketing manager here at EDB. I'll be your host today for our webinar, Comparing Physical and Logical Replication for PostgreSQL. I'm joined by Simon Riggs, Postgres Fellow at EDB. Before I turn it over, I'm just going to go through a few housekeeping items. This presentation is being recorded, and we're going to share the recording to the email address you used to register for the webinar after today's session. All of your lines are currently muted. If you have a question, please feel free to submit it in the question panel. We expect our presentation to last most of the time today, but we'll allot any extra time to answer as many questions as we can. And with that, I will hand it over to Simon.
Thank you very much, Courtney. So we're going to be talking today about high availability and replication with a specific topic being the comparison of physical and logical replication techniques in PostgreSQL. But before I go into that, I would like to shout out really to friends and colleagues in India because of the difficulties that are being suffered there because of the COVID pandemic. So although it's often seen as an important topic, obviously it's not life and death like what is happening right now in India and other parts of the world as well. So, let's sort of measure our thoughts on that. Anyway, so onwards to the technical topic of the day. So there are multiple ways of doing replication. Why does it matter which one you pick? Surely they're just all the same, aren't they? Well, the first thing that matters is the level of integration with the database, because if it's not in database replication, then it doesn't work the same way. It might say, oh, it's protecting your database, okay, and it probably does do that, but it's missing out on quite a few aspects, quite a few features and performance that you get from properly integrated replication. So there's a very good reason why we spend all of this time writing replication features in the database, and it's not just an operating system feature. Okay, so we're going to talk about the features and the behavior and the maturity of these replication techniques. Now, the first thing to look at is that the technology of replication has evolved over time, and the first attempts in database replication were based on triggers, and although that was a good place to start, it's not the best place to end up. It's not sufficiently well integrated into the database to make a lot of sense, and the overheads of it are large. So in 2 slides, I've already ruled out 2 different types of replication to speak about. That's storage-based replication. I'm not going to speak about at all because it's not sufficiently integrated, and also trigger-based replication for roughly the same reasons. Now, those 2 things have been ruled out for many years as being a good thing to use with database. And as a result, I'm just focusing my attention today on physical streaming replication and logical streaming replication, and mostly talking about what is already in core PostgreSQL. So in order to compare 2 things, you can usually talk about the things that they have in common, so common similarities and advantages. You can also talk about the things that they have in common that are negative, so common difficulties. And then also you can talk about things that logical replication has an advantage over physical, and then advantages that physical has over logical. Now I've tried to sort of phrase that without kind of being negative about one or the other, but there are a few things where I actually need to say this doesn't work very well, in one or other of the technologies. So I do also have some disadvantages, okay, to sort of balance it out. So basically, yeah, we're going to review all of the different features and how they work based on this model. But before I do that, just a word about the terms that we're going to use. In this presentation and other ones, start to talk about the origin node as being the node where the changes originate. Now that is also known as the write node, the primary, the master, okay? But it's actually important to use that word origin because that's something that becomes important when we look at cascading replication. But it also comes in when we start to talk about other issues as well. So origin is the upstream node, target is the downstream node. So the first area to look at is common similarities and advantages of replication. So with both logical and physical replication, the downstream node always connects to the origin nodes first, and they use a standard libpq API so that all security considerations are enforced. So you don't have to give up any security in order to choose this type of replication. Now, replication status information is stored within replication slots, and that means that the status of both types of replication is saved and restored in exactly the same way. And lastly, replication progress information is stored in terms of log sequence numbers, or LSNs, and that means monitoring both types of replication is essentially identical. All of this is obviously very good news. When we apply changes based upon the changes to the origin, we always apply those changes automatically. So there's no sort of there's no handle that you have to move in order to make the replication work. Transactions are always committed in log sequence order. That's the order of the LSNs. And that's particularly important because it ensures that we get consistency across the different nodes. Now, it's difficult to explain that because I don't mean consistency across multiple nodes. I just mean that the order of changes that occurred on the origin is also the same as the order of the changes on the downstream node, and so they are consistent. Sync rep is available in both situations because sync rep is actually based on log sequence number, and so it works fine with logical replication. And that means that both logical and physical support a mix of async and synchronous transactions on the origin. Both forms of replication support what we call single master, multiple standby. So that is a well-used architecture in database replication, and both systems support that. Now, there are some advantages that you get with logical standby servers, and we're going to mention those immediately by talking about what the advantages are of logical replication. So when you use logical replication, the target node is a full write node. And that means that we could write any type of data at all on those nodes. Now that gives a whole list of different advantages. We can have new different indexes on tables. We can have temp tables. We can allow serializable transactions. We can allow prepared transactions, as well as listen and notify. So that's quite a list of restrictions that you get with physical, or we can view them as advantages of logical, depending on which way you see that. Logical replication itself means that we only send the actual logical changes. That means the data that we would put if we drew a data model of the database. So all of these other ones and zeros, I've kind of tried to sum that up with that little picture there. So things like when we vacuum a table, when we freeze rows, when we set hints, are all avoided when we do logical replication. In fact, they're filtered away, right? And that means that the amount of data that we're sending across the replication link is much lower when we have logical replication. And that's particularly important when we consider things like full page writes, because they occupy a very significant amount of space within the transaction log, and also index changes. So the situation there is if I'm sending an insert into a table with 5 indexes, physical replication will send the change itself and then 5 index changes into the transaction log, whereas logical will simply strip out all of the index changes, send just the insert across to the other side. But then, of course, if the indexes are the same, when you apply the changes, you'll also have the index changes to make as well. So logical replication supports upgrades without downtime very easily. And that was one of the main reasons why we wanted to really to introduce this new technology. So upgrading from Postgres 11 to 13, for example, is particularly straightforward just by using logical replication. Logical replication also allows you to do selective replication, where you can choose which tables or rows will be excluded from replication, which can obviously be very useful in certain circumstances. Now, when we apply changes from the origin, the changes when we do logical are not replicated until after the commit. Now that is useful because it means rollbacks and aborts are not replicated. It can introduce a small additional latency as well, but that's typically not that large, and so we won't mention that. But what I will mention is that larger transactions do benefit from streaming prior to commit, and that's why there's a new feature in Postgres 14 that allows you to stream transactions before they've committed. Now, the best way to go about that in terms of logical replication is just to make your changes in smaller transactions, and that allows those then to be streamed fairly easily. Okay. So it's in the advantages section, but it's kind of a disadvantage of logical. What logical does allow is a number of different new architectures. You can more easily broadcast changes to a range of different databases, or you can roll up information, taking multiple sources into one hub as a way of collecting data from multiple different places. So those are some advantages of logical replication, and I'm trying to give a balanced viewpoint, so I won't sing the praises too much of that. But the point is that there are significant reasons why we would want to replicate things in a logical manner. But we need to talk about what difficulties we have with replication as well. Now, some people have said, oh, well, I wouldn't want to do logical replication, or I wouldn't want to use BDR because conflicts can happen when you use multi-master systems. Well, actually, all replication techniques cause conflicts of some kind or another. And I'd like to draw your attention to the fact that physical replication does have replication conflicts that can cause either replication to halt or actually for certain queries to be cancelled and disconnected from the server. So when a vacuum command truncates files on the origin node, that can affect things on the standby, because it can introduce access exclusive locks which prevent selects from working. You can get something called a snapshot conflict. Now, it's possible to avoid a snapshot conflict by turning hot standby feedback equals on, but that gives a different problem that I'll mention on the next slide. But my point here is that no matter what type of replication you choose, there are behaviors that you need to take into account when you're running the database. It's not simply possible to just say, conflicts only occur with logical or conflicts only occur with physical. That's not true. So long-running transactions give problems for both physical and logical. Now, if you use hot standby feedback, then what that means is that a select long-running transaction on the hot standby will actually hold back the xmin value, which means that it will prevent the removal of dead rows on the origin node. So there is a physical effect of setting hot standby feedback equals on. So that then gives you a choice of problem. Do you have snapshot conflicts, or do you have preventing the removal of dead rows? So there isn't a perfect world there. You've got to make choices as to which negative you find the most acceptable. And then on the logical side, long-running transactions can also cause problems. Now, these are completely different problems. So on the physical side, we're talking about selects running on hot standby, and on logical replication, I'm talking about write transactions running on the downstream nodes, or sorry, on the origin nodes. So they're completely different behaviors, but what I'm saying is that both physical and logical suffer from some impact of long-running transactions. And as I mentioned earlier, long write transactions can give poor performance and latency when using logical decoding or logical replication. Now, there are some solutions to that, but that's the main, it's an issue to be solved, okay? So locking is also something of an issue, in the sense that when you lock a database table or a row on one node, it doesn't necessarily lock all of the other nodes. Now that's a good thing and a bad thing, but it's worth understanding that those locks aren't propagated, and that might give you some kind of consistency problem. So it could be good or it could be bad, but it's roughly the same between physical and logical replication. So now let's move on to talking about some of the disadvantages of physical replication. Now, before I do that, I just wanted to check whether there were any questions arising from that.
Don't see any that have been submitted yet.
Okay, no worries. I'll press on. Okay, so so now we're going to talk about the disadvantages of physical replication, and some, mention some things that maybe people are not aware of. So physical replication does require that the configurations between the servers are quite tightly coupled, in the sense some things need to be identical, such as the major version, and then there are other parameters that need to be set to at least the same level or higher on the standby nodes. And that is specifically max connections, max worker processes, max well senders, max prepared transactions and max locks per transaction. Now, if you change any of those on the master, it will send a message to the standby nodes. And prior to Postgres 14, the node just simply shut down, which wasn't particularly useful. So in Postgres 14, if you change a parameter in a way that conflicts with the parameter setting on a standby, then it will just pause the standby. So at least the server's up and running, even if it's not able to apply transaction changes. Now, we have looked quite hard at how that worked, and I did propose some patches, but the overhead of those patches was pretty ridiculous. So it's just simply not feasible to decouple those things. Another thing that we need to mention is how hints work within data blocks. So Postgres uses a scheme called hints, where when you read a row that has just been written, it will set a hint on there to say whether or not the transaction has committed or not. And that causes a very small write to the database blocks, which usually doesn't matter at all. But the point here is that we don't generate WAL records in all cases, okay? And we do generate them in some, in the sense that we will generate a full page image just for a hint if you have database checksums enabled. But the issue that's caused with physical replication is that B-tree indexes cannot trust that the item killed hint has been correctly replicated, and as a result, B-tree searches are less than optimal in a table with updates. Specifically, the B-tree search will need to search more database rows in the heap, I mean, before it will give a full and correct answer to the query. And what that means is that B-tree scans against non-unique indexes, or in some cases unique indexes, will cost more on a standby than they did do on the origin node. Okay, and in some cases that might be twice as slow, for example. So there is a noticeable performance issue when you run index requests on a standby. No, it's noticeable. It's not awful. It's just noticeable. Okay. So Vladimir's asking, will I address connection pooling and load balancing in this context? Yeah, I mean, I don't want to say that connection pooling is not important. It very much is. But in this particular presentation, I'm contrasting physical against logical replication. So I think that we probably need a whole new presentation about connection pooling and load balancing as regards high availability. But we'll do that another time. Okay, so really for now, I'm just talking about the two different types of physical and logical replication. Another situation that can occur with physical is something called a split brain. Now, actually, this can occur in any replication system where you have a single master and you're failing over to a standby node, so which could also happen in a logical context. And if you do that, it's possible that you can end up with two nodes, each of which have got slightly different last few transactions on. Okay, and the only sensible way to cope with that is to actually wait a period of time before you do a proper failover, because there's no easy way to determine that all of the records that you have are present. Now, because there's no easy way, that means we have to wait, and that means that single master techniques will always have a longer period of time to wait when they do a failover. Now, it isn't related to the speed of the failover. I'm just saying it's related to the certain knowledge that we have about whether all of the data has arrived or not. Okay. And that can be a tricky situation, which causes a longer period of waiting than we might expect. So actually, the failover of physical replication does take a very short period of time, but that's not the period we need to measure. The period is the amount of time we need to wait before we do the full promotion of the standby node in order to get the failover to succeed. Anyway, just to say that BDR does cope with this situation. It can resolve split brains, but it can also switch very quickly from one to the other without waiting, and it's a particularly important point. So let's talk about advantages of physical replication, because there are some, and we need to cover what those are. Well, one advantage I've heard of physical replication is it just works. And I think what people mean to say by that is that there's no complexity involved. It's trivial, and it just works every time. Well, really, we've spent, physical replication came out in 2010, and every single release since then has had major bugs and tweaks to physical replication in order to get it to work better. Okay, so my view as a kind of insider on what's gone wrong and what's gone right is that physical replication was good. It was certainly the best we could do at the time, but we are able to deliver a different type of system now. So the "it just works" argument doesn't really fly with me anymore. What it does do is it has fully automatic replication of DDL, which logical replication does not yet have. But that is a solved problem with BDR. It is, by the way, a complex problem as well, which is one of the reasons it's not yet in core Postgres. Another advantage of physical replication is it allows you to run multiple databases on one instance in a much easier way. Some people do that, but in general, it's not advised for people to do that. So it's not specifically a good reason to use physical replication, but it might be the most important thing for you. There's a number of things that are not supported on logical replication, and as a result of that, these become advantages of physical replication. So materialized views don't work in the way that we would like them to, and also updates and deletes are only possible with logical replication when you have a primary key index, because you need that to be able to identify the row. Now, actually, BDR does support updates and deletes without a primary key, because that's quite an important use case for some very large databases. But we do need some form of index, even if it's not a unique index, because obviously otherwise it would just be too slow on a large database. There's a number of features that are supported by physical replication that don't occur with logical replication, and that's with OIDs. Now, I know that was removed in Postgres 12, so I'm really talking about Postgres 10 or Postgres 11 there. The large object interface does not work with logical replication and is never likely to. And essentially, that's mostly deprecated feature these days anyway. And the last one is rules that execute only on a replica or execute at all on a replica Now, these were only ever needed for trigger-based replication anyway, so they don't really make sense to use with logical replication. And rules themselves are very difficult to use and mostly deprecated anyway. So these issues are not really anything that we need to worry about. So there's a couple of questions. How to verify a split brain. If you do get a split brain, then you need some kind of comparison utility that will look at your database and find out what changes were made to the database and work out where the rows are that are missing. Now, open source Postgres does not have any kind of utility along those lines. EDB does have a tool called Live Compare that helps with that if you need it. But obviously it's difficult to cope with a split brain. The point is, after you've done an emergency failover, you'd like to find out what records are changed very quickly, and yet you're really unable to do so because the comparison utility doesn't run that quickly. It's not instant, for example. So Clinton's asking, is the potential for poor performance on a standby with respect to B-tree indexes mitigated by B-tree improvements in version 12 and version 13? Not at all, no. This is a problem that still exists in version 14. Somebody else is asking, does BDR replace XDB? And both of those are EDB products. And yes, BDR is the strategic replication technology for EDB and does effectively replace XDB as a multi-master solution, but XDB does a number of things that BDR is not designed to do. For example, migrating between heterogeneous data stores, for example, Oracle to Postgres or Postgres to something else, can be executed using XDB. So they end up as being different products. Okay. If the replication breaks, we have to start from scratch. I'm not sure I understand that question. Right, so that's a good question from John Lovato. Not to say all of them aren't good, it's just I understand some and not others. Are there any types that cannot participate in physical or logical replication? That's a very good question, because what we need to understand with the way that logical replication works is we translate the data from how it's stored in the database into its text representation when we transfer it down the logical replication link. So all data types work with logical replication. Okay, so you're not restricted to a specific a small subset of data types, but in all cases, in either both logical or physical replication, you need to have the data type installed on both nodes. Okay, now you can have a different version of the data type installed on a logical replicated link, but not a physical one. Okay. Right, so I'm not talking in this presentation anything at all about Kubernetes or orchestration technologies. I'm simply talking about the underlying physical technology of replication itself. Okay. Are there any issues with partitions? Yes and no. So logical replication did have a slight problem previously when you were replicating from a table that wasn't replicated to a table that was partitioned to a table that wasn't, and the other way around. That problem is now solved, and we're able to route changes from tables that are not partitioned to a table that is partitioned. Okay, so Ramesh is talking about the time taken to rebuild standby databases using PG-based backup. Well, there are other ways of doing that, but clearly what we need to use is a parallel base backup technique, and we'll see more of that in the future. Soyan is saying, does the logical replication allow bidirectional replication? So the in-core logical replication does form the basis on which we build BDR, but the in-core technology itself does not support bidirectional replication. So logical replication not following physical replication is a major disadvantage. And I do expect there to be a solution in core one day, but so far people have blocked those solutions going in, and they have been presented, but we will eventually get that into core Postgres. Yes, the DDL needs to be the same on the origin and the target nodes in order to make logical replication work, but that's also true with physical replication. So there's no easy thing to do there. BDR does support disparate replication in the sense that you can replicate from one table to another table with columns added. Okay, so that's quite an interesting additional feature with BDR. So the questions are coming thick and fast now, so I'm trying to work my way through them before we get too far. So does BDR work with both community Postgres and EDB EPAS? Yes, is the answer. And then you're going to say, so which version and that kind of thing. So BDR works with EPAS as of the 3.7 release, which is in mid-May. So we're about 3 or 4 weeks away from that being released. I can tell you it does already work perfectly fine, but the actual release is not yet out. So Henry is saying, when replication pauses because of differences in parameters between origin and target, what do you do? What you do is you set the parameters on the target node and then restart the server. So there will need to be a restart in order to pick up those new values of the parameters. Okay, well, thank you for all of your questions. I can't answer them all quickly. I can't even read them all that quickly. So I'll just press on with the rest of the presentation. So I hope that's kind of answered a few of your questions as we go through. Now I can't get rid of the list of questions. So. Okay, so what I wanted to talk about now is replication architectures and how that affects performance, because this is also an important concern. So in terms of the topics I have left, I'm going to be talking purely about the performance of physical versus logical replication, and then sort of end up with a summary few slides. So I've got 8 slides left to go, and we should be finished within the next 20 minutes. Okay, so just to sort of give you an overview of where we're going with this. Obviously, there's a lot of questions from people, and they're all valid questions. It's just I can't cover the whole of every aspect of high availability and replication within a 1-hour presentation. So other presentations on this topic will follow. So I expect to do a webinar roughly monthly on these things, and we'll get all of those questions answered in time. Okay, so I'll just press on to talk about replication performance. So replication architectures, it's important to understand how the replication mechanism works in order to understand performance. So with physical replication, the data blocks are passed directly from the origin to the target, and those changes are applied to specific block addresses, which means that we're able to just look up that one block. Okay, so I've said that that's got a complexity of 01, meaning it's the time to access a data block is effectively constant, and we just go and get that data block and make that change. Now that doesn't include IO, but IO is similar between logical and physical, so I won't include a discussion of that. In logical, when we apply changes, we need to locate the row that would be changed. So if you're doing updates or you're doing deletes, then you need to find the row before you can update it. And that means that we need to do some kind of B-tree lookup in order to locate the row, and therefore it isn't always immediate to look up the row. It means we have to descend a B-tree, which means that it's slightly more costly. Now, here's the difficulty in understanding which one will be faster, physical or logical, because physical is much faster per block, as I'm showing you here, but physical needs to apply more blocks. So in a situation where there are many vacuums running, you'll often find that physical replication will run more slowly than logical replication, whereas when those vacuums are finished, you might find it goes the other way, and a logical replication would be slower than physical. Okay, so actually it's quite workload dependent whether physical or logical replication is the faster of the two mechanisms. But in both of these cases, we need to take into account how these systems work with respect to the amount of IO that they need to perform, because obviously both forms of replication work better when you're replicating something that fits easily within memory. So physical streaming replication has an architecture like this. We make changes on the origin, and that writes transaction log or WAL data to a file, which is then read by the WAL sender process, and that data is then sent across the replication link to the downstream server, or where it's picked up by the WAL receiver process and then written to the WAL file again on the other side. That WAL file is then read by the startup process, and those changes will be applied to the database. So there are some dedicated processes that spend all of their time sending data from one server to the other, and that's why we're able to do low latency replication, what we call streaming replication. Now, the design of logical replication is similar. We use a WAL sender process, exactly the same purpose, to send changes down the replication link, and then we have a different type of process which applies the changes on the apply side. Now, you'll see that the physical and the logical are actually fairly similar in their architecture, and that we want it to be as similar as possible. There's no reason to make them different just because we could. But what that means is that both of those architectures can be slowed down if we need to do excessive I/O on the target node. And so one of the things that we need to look at is, does this system work in parallel? And if we look at the number of processes involved in both, you'll see that physical streaming replication uses one process upstream and two downstream, and logical streaming uses one process upstream and one process downstream. And that's why in BDR, we use logical streaming replication with multiple processes so that we're able to process the data flow in parallel and thus get higher performance. Okay, so just to say that in both cases, I/O is a problem and needs to be addressed. Now, there's a change just gone into Postgres 14 to improve the speed of physical streaming replication, and that's good. But there are still some linkages that mean it doesn't work as well as we would like. So there's still more work to do on both. Okay. So my conclusions really is that the maturity of replication systems for databases has definitely moved forward over the years, but there's still quite a lot more work yet to do on both physical and logical replication. Now, some of that work has already been done in terms of the BDR product, and we do expect that some of that work, or eventually all of that work, will go through to Postgres core, but actually that will take quite a long time to feed back all of those changes. But in terms of maturity, we can see that physical streaming replication is becoming more stable. It's becoming, after 10 or 11 years, it's now becoming a little bit more stable. But there are still bugs and new features required to make it really work well. And I've identified quite a few of those problems here. So it's not that it's buggy, it's just that it needs specific tuning to make it work properly in certain cases. Now, logical streaming replication is, you might say, is mature in a different way, in that it's a more advanced design. That doesn't mean it's more complex, it just means it's a more advanced design. The thinking behind it is more advanced, which was arrived at reusing some of the techniques and code from physical streaming replication. And that's also reached a much higher level of maturity within the BDR product range. But obviously I don't want to talk about that exclusively. But just to say that in terms of maturity, really both technologies have attained a level of maturity, but there are still downsides really in both cases, and you need to consider which ones that you might want to use and how that affects your applications. And what I wanted to do here was just use a graphic to show you that with logical replication, a lot of the features from BDR have been broken off piece by piece and pushed through into Postgres core, and that's continued over the last 9 separate releases of Postgres, and continues still. Okay, so my ending note really is to say that logical replication is an exciting technology. It's very viable for your use. But there's still things that we need to do to improve it. But the same is also true with physical streaming replication, in that there are significant disadvantages to both. Now, I think the end point here really is to say that there is no free lunch. Any form of replication technology that you use will have some kind of impact and some kind of cost in your applications. And when you're running a major database application, you need to take into account how the replication systems work in order to understand what happens underneath the cover. So no particular surprise there. If you drive a car, sometimes you need to know how engines behave, and that's exactly the same is true with the database engine. So if there are any other questions, I'll come back to that. So yeah, John Lovato is saying, is it possible to set up cascading replication using physical replication? Yes, cascading is supported, but with logical replication, we haven't yet worked out how to do cascading replication. We will do. It's not especially difficult to make that work, but we will eventually get that to work. So you're saying it means that in both cases, master sends same amount of data. No, very specifically, I'm not saying that. With physical replication, the origin node or the master node sends quite a lot more data than is sent with logical streaming replication. So physical replication definitely sends a lot more data. Okay. So can triggers fire off in all replica types? It's a good question. The answer is no. In a physical standby, you can't fire a trigger on apply on the standby nodes or the replicas. Okay, so triggers can't fire in all cases, but they can fire with logical replication. Right, so remounting the Postgres data folder from another server in the same place. Yeah, I mean, the replication in that particular situation doesn't work in the way that you think it might. So that's not easily a viable option here. So. Okay, so are there any other questions that you'd like me to cover before we end up the session? I'm sorry if I've not been able to read all of your questions, but I have gone through as many as I can sensibly answer usefully within the time. So, and I guess that we'll probably write a blog covering some of the points mentioned here.
Yes, exactly. Thank you so much, Simon. And if we didn't have a chance to answer, we'll be reviewing any questions we didn't answer live after the session. Just as a reminder, you'll receive a recording of the session to the email that you used to register later today. So thank you, Simon, and thank you for everyone for joining us live today. And we hope to talk to you all soon. Thank you.
Thank you very much, everybody. See you again soon.